Imagine a universe where you can see the stars, map the galaxies, and count every atom in your own body. It sounds like science fiction, right? But here is the reality. We are blind to 95% of the chemical activity happening inside us right now. In our labs today, we have cataloged over 16,000 endogenous metabolites, thousands of drugs, and tens of thousands of food constituents. We have the tools, the databases like HMDB and DrugBank are exploding with data. Yet when scientists look at a sample of human serum or saliva, they see a landscape dominated by invisible dark matter. Up to 95% of the peaks in our mass spectrometry data remain unassigned. These are not just missing numbers. These are silent players that could be holding the key to curing Alzheimer's, understanding cancer metabolism, or explaining why some people respond to drugs while others don't. Today, we are peeling back that veil to see what is hiding in the dark metabolome and why this invisible frontier is the most important place for biology to focus next. The situation might seem like a paradox on paper. On one side, you have an unprecedented data explosion. As of early 2026, databases are growing at a frantic pace. We now track over 16,000 endogenous metabolites in the HMDB alone, alongside massive inventories for drugs and food constituents. The University of Alberta has been systematically characterizing biofluids like cerebrospinal fluid and urine with incredible precision. Simultaneously, we have resources like T3DB covering thousands of toxins and SMPDB mapping over 132,000 metabolic pathways across organisms. It feels like the library should be full. Yet, when you actually run a sample through a modern instrument, the results are startlingly sparse regarding identification. Despite these massive catalogs growing steadily, up to 95% of the peaks detected in many samples remain unassigned. This isn't a failure of our instruments. Mass spectrometers can detect thousands of compounds per second with high sensitivity. The gap is not in detection, it is in recognition. We are seeing a signal that we simply do not have a name for, or worse, a structure for. It suggests that the known universe of chemistry inside us is just a small island floating in an ocean of unknowns, and our current maps aren't detailed enough to chart the coastlines. Why does this matter if it's just unknown data? Because biology rarely happens with everything known. In cosmology, dark matter is estimated to make up more than a quarter of the universe's mass, acting as the mysterious glue that holds galaxies together without us ever seeing it directly. There is now a compelling argument that chemistry has its own version of this phenomenon: dark metabolites. These are likely thousands of small molecules present in bone and other tissues, perhaps synthesized by our microbiome or produced through novel enzymatic pathways we haven't discovered yet. If 95% of peaks are unassigned in serum samples, it implies a massive layer of biological regulation is operating without us knowing the players involved. Consider drug metabolism. When the FDA releases new guidance on safety testing and metabolite identification, they are essentially asking us to look for signals that might be these dark molecules. They could be toxic byproducts that current databases like DrugBank simply don't have entries for yet. Ignoring them is risky because if a drug interacts with an unknown enzyme system producing a dark metabolite, we could miss side effects entirely until it's too late. The invisible glue isn't just structural, it might be the regulator of our cellular health. So how do we catch what is hiding? The challenge lies in the sheer complexity and the dynamic nature of these samples. We are dealing with a soup where thousands of compounds overlap, ionize differently, and shift concentrations based on diet, time of day, or genetic variation. The recent push for new tools isn't just about bigger computers. It requires fundamentally different approaches to structural elucidation. Scientists are no longer just matching peaks against existing libraries like FoodDB or SMPDB because those libraries, while vast, covering 70,000 food components and thousands of pathways, are static snapshots in a dynamic world. A metabolite today might not be on the list tomorrow if our biological state changes. The solution involves moving toward non-targeted analysis where we prioritize finding the structure over matching a known ID. We need to look at the odd peaks that don't fit the standard narrative of known pathways. It requires a shift in mindset. Instead of asking, "What is this peak?" we must ask, "What could this unknown molecule be doing?" This is where the real discovery lies, not in confirming what we already know, but in daring to propose structures for those 95% that have been sitting silent on our screens for years. The practical implications of cracking the dark metabolome are staggering and immediate. If we can identify just 10% of these currently unassigned peaks, we could revolutionize personalized medicine. Imagine a scenario where a patient's blood profile shows a specific pattern of unknowns that predicts a response to chemotherapy or reveals an early-stage metabolic disorder before symptoms appear. Currently, our safety testing protocols for drugs are retrospective. We analyze what we know after the fact. The new era demands prospective identification. By integrating advanced AI prediction models with experimental validation, we can start to assign those mysterious peaks names and functions. This means moving from a database of knowns to a predictive model of biological possibility. It transforms how we view safety testing under FDA guidance. Instead of checking boxes for known metabolites, we would be monitoring the entire chemical landscape for any deviation in the dark sector. The next decade of pharmacology and biology won't belong to those who catalog what is visible, but to those brave enough to illuminate the 95% that has been holding its breath in the shadows of our own bloodstream. We are standing on the brink of a massive expansion in human biology, but we can only see the tip of the iceberg if we stop looking at the water beneath it. The fact that 95% of metabolites remain mysterious is not a limitation. It is an invitation. As our databases grow to include tens of thousands of pathways and food components, the gap between what we know and what exists in our bodies becomes even more profound. This video highlighted how the dark metabolome challenges our current tools and why embracing this unknown is essential for future medical breakthroughs. If you want to stay ahead of the curve on the latest discoveries in biochemistry and AI-driven science, make sure you hit that like button and subscribe right now. Drop a comment below telling me what other areas of biology feel mysterious to you, because we are all just beginning to solve this puzzle together.